Okay, so let's start with a gentle introduction to tropical geometry. The slogan of my lectures this week is tropical geometry is a combinatorial shadow of algebraic geometry. So the goal is to solve problems in algebraic geometry using combinatorial techniques. And so I'm going to wave my hands slightly here, and then I'll stop waving my hands in a slide and be much more concrete and down to earth. But the idea here is we might have an object from algebraic geometry, like an elliptic curve, which is shown on the left, and we want to know something about it. Tropicalization is going to be a procedure that takes this variety and converts it into a combinatorial shadow. So the combinatorial shadow is going to be this picture on the right, which is what we call a tropical elliptic. So, and the idea is that this picture on the right will keep some of the information about the original curve. For example, we started with a curve and we have a one-dimensional object here. Elliptic curves are genus 1, they're topologically a torus. And we remember that from this circle here in this picture. I've drawn you a picture of an elliptic curve in the plane. So it's embedded by a polynomial of degree 3. The solutions to a polynomial of degree 3. And that degree 3, we remember, is also encoded in this picture, in this case by the 3 directions going up, to the right, and down. And some of these things I'm going to say more concretely today and Thursday, and some of them you'll hear later in the series, perhaps next week. Should also say there are many approaches to tropical geometry, and this approach, for this week, we're going to be in this, what I might call the embedded approach. We're going to regard the varieties we study as subvarieties. Here's somewhere. In the interest of keeping this week as accessible as possible, we will just look at affine varieties, subvarieties of affine space. That actually has 95% of the content. Those of you who are more sophisticated may want to think about how we could replace these by toric varieties and affine space by toric varieties and more complicated things. But just because I talk about affine space this week, you can rest assured that there is a bit more going along under the hood. I should also, though, have a disclaimer that, I just said on the previous slide, tropical geometry is a combinatorial part of algebraic geometry. Really, it's a much broader field with applications inside and outside mathematics. We're not going to touch on them so much at the start, at least in the currently planned part of this lecture series, but they are really fascinating and interesting, and I encourage you to investigate them. So I'll just touch on just throw out a few words to give an idea. So there's applications, for example, in economics. So Paul Klemperer at Oxford was involved in pricing auctions for the Bank of England during the financial crisis, using some ideas from tropical geometry. In optimization, so optimization over the tropical semiring, which we'll meet in a moment, or otherwise known as the max plus algebra, is much older actually than tropical geometry. And for example, it was used to design the schedule for the Dutch railroad, the Dutch railways at one point. More recently, the ideas that we'll meet this week have been used in some more theoretical ideas in optimization. In machine learning with neural networks, one of the popular activation functions is ReLU, and the functions that you get out of a neural network in that sense are exactly tropical rational functions. We get applications to phylogenetics, and then I've just put a ... because there are many more. So what you should take away from this slide is I'm going to tell you about, and then people in the future, in the weeks that come, are going to tell you about tropical geometry inside algebraic geometry, but there's much, much more that you could also learn. Okay, so now that was the head-wavy overview. I now want to sort of really start with the proper school part and with formal definitions. And I encourage you, please do, ask a question if you need to interrupt in the chat or as we're going. And I will pause at a few moments from now on for some questions as well. Okay, so we're going to start with the star of the piece, and that's the tropical semiring. One way to describe tropical geometry is as algebraic geometry over the tropical semiring. So this is R union infinity with operations tropical plus, which is minimum, and tropical times, which is usual addition. So for example, we have 5 tropical plus 8. That's in usual arithmetic. It's the minimum of 5 and 8, so it's 5. 3 tropical times 8, that's 3 plus 8 is 11. And now we check things and we say, for example, 3 times 5 plus 8, all tropical operations. 5 plus 8, that's, we've already decided, is 5. 3 times 5, that's 3 plus 5 in usual arithmetic is 8. But on the other hand, if you go 3 times 5, that's 8. 3 times 8 is 11. And the minimum of 8 and 11 is 8. Okay, so we get the same answer on both sides. And so you can see what we've actually seen is that tropical multiplication distributes over tropical addition. Okay, so just maybe reality check to check we're all on the same page. If I ask you for 6 tropical times 5, tropical plus 10, what does that equal? So maybe we'll pause until a few people type an answer in the chat. So what is 6 tropical times 5, tropical plus 10? Someone has to be brave and actually chat, or am I not seeing the chat? Hannah, you will tell me if people have someone's chatted an answer correctly. Someone has chatted an answer correctly. Okay, good. Oh, good. Oh, I see lots of answers. Sorry, the chat wasn't just updating for me correctly. Perfect. Good. We all agree. The minimum of 10 and 11 is 10. Perfect. Good. What do I want you to notice about this? So we can all do the arithmetic, and we notice that this is commutative. So minimum is commutative. Addition we already knew was commutative. It's associative. Infinity is the additive identity. Okay, the minimum of 7 at infinity is 7. And 0 is the multiplicative identity. So 29 times 0, in usual arithmetic, that's 29 plus 0, so it's just 29. So 0 is the multiplicative identity. The only thing we're missing is that there's no subtraction. Okay, so that makes this into a semi-ring. So the idea is here, addition makes R bar, so R union infinity, into a monoid, an abelian or commutative monoid, but not an abelian group. So we're missing subtraction, and a semi-ring is something that satisfies all of the axioms of a ring except for addition is a monoid except for a ring. Sorry, addition is a monoid instead of a group. Okay, so that's the tropical semi-ring. Yes, questions, comments? Okay. In algebraic geometry, we want to think about polynomial functions. So we'll look at the semi-ring of tropical polynomials. The first thing you notice is that tropical polynomials are piecewise linear functions. So for example, if I have f being x cubed plus x squared plus 1 times x plus 4, in usual arithmetic, that's the minimum of 3x, 2x, x plus 1, and 4. And so I've drawn a picture here. We have the line y equals 4, y equals x plus 1, y equals 2x, and y equals 3x. It's not quite so obvious on this picture, but there is actually a change of slope at the origin here. So it goes, this is the line y in the red, which is the minimum. This is the line y equals 3x, and this is the line y equals 2x. So it changes slope at 0, at 1, and at 3. Okay, so this is a piecewise linear function. So it's piecewise linear because each of the monomials in my polynomial become a linear function. And then we're taking the minimum of them because it's the tropical sum. And so we're getting that.
Diane, there's a question in the chat whether the tropical Semiring could be defined over an ordered Semiring.
So defined over, so there are definitely, so you want to replace R with an ordered semi. So so you can definitely generalize this a lot. One thing we often want is additively, we want to replace it by an arbitrarily additively idempotent semiring. Sorry, so this is additively idempotent means one thing you notice about the tropical semiring is that A plus A equals A. And so anything like any additively, and sometimes we want semi-field. So we like the fact that multiplication every non-zero, so non-infinity element is a field. Sorry, it has a multiplicative inverse. Yes, and someone's saying we can't find a real number B such that the minimum of A and B is infinity. Yes, yeah, great. Okay, so here we have our picture of this. What if we go to more variables? Then we might have polynomials like 3 times x1 squared plus 5 times x1 times x2 plus 7, where all my operations are tropical operations. So in usual arithmetic, this is the...
Diane, there's another question in the chat, which I'm not sure I understood it. Question from Felix, is it the derivative of x cubed? Now, I didn't get what the derivative of x cubed is. Maybe Felix, you can tell us again. Oh. NVM?
So I think it's maybe the question is the 3x is not a derivative, it's turning x cubed tropically. So it's x tropical times x tropical times x. Okay. And that is x plus x plus x, which is 3x.
Yeah, in fact, I think we got it already. Mm-hmm.
Okay, yeah. Yeah. And we have multiplicative, yes, exactly. Semi-field is, we're missing additive inverses, but it's a semi-field because we do have multiplicative.
I just mistyped that, sorry, my fault. Additive, thank you, sorry.
Okay, perfect. Okay, so where are we? The tropical, so we have, so I just want to emphasize here, this is x1 tropical squared, so it's x1 tropically times x1. So that's why we have a 2x1 here. So this turns into 3x1 squared is 2x1 plus 3. 5x1 x2 is x1 plus x2 plus 5. Usual arithmetic. So here's the most important definition, and is the tropical hypersurface of a tropical polynomial. That's going to be the w in r bar to the n for which f of w is infinity, or the minimum in f of w is achieved at least twice. Okay, f is a tropical polynomial, so it's a minimum of a bunch of sums. And we say that the minimum is achieved at least twice if when you plug in your polynomial, you're going to get a bunch of numbers to show up twice on your list. Okay. Here's the one most important example that they essentially take away your tropical geometry license if you don't include this in the introduction to tropical geometry. And this is the tropical line. So if I start with x plus y plus 0, so the first thing you notice is 0 is the multiplicative identity, not the additive identity. So I can't just remove the 0. And in usual arithmetic, this is the minimum of x, y, and 0. So if I look at the function here, if I imagine trying to graph it, on the positive orthant, the minimum of x, y, and 0 is 0. On the region below the x-axis, but to the right, the minimum of x, y, and 0 is y. And to the left, the minimum of x, y, and 0 is x. So where is the minimum achieved at least twice? Well, on the positive x-axis, the minimum of x, y, and 0 is both 0 and y. On the positive y-axis, the minimum is both 0 and x. And on the slide y equals x negative, the minimum is both x and y. And then I've got these two dots. This is the point infinity, comma 0, and 0, comma infinity. So those are also points in this hypersurface. We'll see towards the end of today why this is a good definition. So in classical algebraic geometry, a hypersurface defined by a polynomial would just be the points in affine space, or in, if you're working over the complex numbers, in C to the n, that vanishes, so which the polynomial is 0. So this is the tropical analog, and we'll see why towards the end of today. So that's the important definition. Let us, don't give away the punchline yet. I should have said, actually, for those who hadn't already seen it, these slides are already posted on the Atom webpage, and if you've already joined the Piazza group, they're also on the Piazza page. Right, and there was a question, infinity is not achieved. Yes, in the previous example, x, y, and 0, because it's a minimum of x, y, and 0, it can never be infinity, because it'll always be at most, it'll always be at most 0. Good. Okay, here's our reality check. The reality check is, what is the variety of 5x squared y plus 2? So we're going to actually treat this seriously as a school. I am going to pause for a moment, give you a moment to actually draw a picture and see how we go.
For the last example, it's true that infinity is not achieved. So why are those points included? This probably refers to the infinite points.
Right, so if we look at the point, so while everyone else is doing that question, I'll answer, is it Francis's question? Infinity, comma 0, that is in the variety because the minimum is achieved twice. It's achieved at 0, at y and 0. It's not that so f of infinity, comma 0 is not infinity, comma 0 is 0, and that minimum is achieved twice. Okay, so hopefully people have had a time to, during this, to start to try and draw what is the variety of 5x squared y plus 2. And the idea is we should see a picture looking something like this. Okay, so it's just going to be a line. And that's because what do we want? We want, in usual arithmetic, this is the minimum of 5 plus 2x plus y and 2. And if we want the minimum to be achieved twice, well, they have to be equal. So we get this equation, which I rewrite as the line y equals minus 3 minus 2x. Okay, so any questions, comments about the definition? Okay, it's a question. Oops. If it's a monomial, does it have a tropical hypersurface? So then, if it's a monomial, you're not going to get the minimum achieved twice. You have to go for the f of w equals infinity. Yeah, and we don't have real curves like, so we're only going to get, so we'll see on Thursday that, I mean, you're going to see from the pictures, we're always going to get, for hypersurfaces actually, you can already see, we're looking at the minimum of piecewise linear things. So we have a piecewise linear function. We're looking at when it is not linear, you're going to get a union of polyhedra. So we will not get things like circles, if that's correct. And we'll see on Thursday that this generalizes, this is a more general statement about tropical geometry. Okay, just show you a few more examples. Yeah, so yes, and what is meant by the minimum achieved twice? This is an important question. Yes, the minimum has to be achieved at 2 different monomials. So we saw in, maybe in this thing, we needed it to be x equals y less than or equal to 0, or y equals 0 less than or equal to x, and so on. Okay, I'll just show you a few more pictures. So that this slide and the next slide you're not meant to be able to actually see in real time, but we will get you, but it's just to give you a flavor of what might happen. So here we have a picture of a plane cubic. So this is like the elliptic curve I showed you before. And we're going to get a picture with this pretty honeycomb picture here. And if you download the slide, so a challenge exercise, if you download the slides later, see if you can verify that this is the picture. And here's one, this time of a quadratic in 3 space. So you're meant to, takes a little bit of practice to realize that this is a picture in 3 space because there's some translucency. But you can see that we have a polyhedral piece going in this direction, another one coming out here. So out here, there's a little square in the middle, and so on. So this is going to be given by this quadratic in the plane.
There's another question, Diane, about the minimum of x and x.
Right, so is the question, I think, if suppose I had the function x squared, which is 2, I see what the minimum, yeah, so I think maybe someone is answering the question, I see. So if f is x plus 1, then trop f should be the minimum of x and 1. Yeah, it's the minimum of x and 1, because we turn into, so it's the minimum of, it's x tropical plus 1 is the minimum of x and 1. Okay. And then the minimum of x and x, oh, I see what you're saying. You're saying, this person's saying x plus x is x. I guess we want to think about usual polynomials here. So we won't have x, yeah, we wouldn't have x tropical plus x unless we meant 2x. So I guess in this case, we think about polynomials as we would normally write them. Okay, what to do just what, before we move on to more variables though, I want to do one more kind of fun exercise, which actually shows what's coming a little later as well. And that's the tropical quadratic formula. So if I start with a polynomial like ax squared plus bx plus c, which in usual arithmetic we can write as the minimum of 2x plus a, x plus b, and c, then you can see I've drawn this in the picture here. I had to make a choice to draw this because you can see that what picture I actually see as the red is the minimum, and what picture I actually see is going to depend on how large b is relative to a and c. As you can see, here's my line y equals x plus b. If b was large, that would be so large that we wouldn't even see the minimum. It would, and the minimum would just be given by the lines y equals c and y equals 2x plus a. Okay, so if I look at this though, as I've drawn it, classically a hypersurface is the zeros of a polynomial. In one variable, that means the roots of the polynomial. So my tropical hypersurface in a polynomial of one variable should just be the tropical roots of that polynomial, which is why I've written kind of roots in quotes here. And if we look at this picture, you can see the minimum, when b is small enough to be in this range, the minimum is going to be achieved if you do the algebra at this point c minus b and b minus a. So those are the 2 points where the minimum is achieved twice, where we're on both of these lines here. And if you further do the algebra, you'll check that that happens when 2b is less than or equal to a plus c. Okay, but if b gets large, so this line disappears, we would only see this point here, this half c minus a, and that's going to happen if 2b is at least a plus c. So I want you to notice 2 things here. The first is 2b, that's tropically b squared. Okay. And a plus c, that's the usual arithmetic way of saying the tropical a times c. So which case we're in depends on the relative size of tropical b squared and ac. This should not surprise you, right? The one thing, it's always difficult in a slightly general audience talk to say something like, as we all know, but the one thing I'm sure you do all know is the usual quadratic formula. So we know that there we care about the discriminant, b squared minus 4ac, and here in the tropical world, we're suddenly caring about tropical b squared and tropical ac and their relative size. So you can see that there is a connection. Where did the 4 go? Well, maybe we see a hint of that later. Okay, that's the first thing you should notice here. The second thing you should notice is while I'm confident everyone does know the quadratic formula, I'm equally confident that in a group this size, while many of you know that there is a cubic formula, most of you don't know the cubic formula, right? Myself included. However, you can see that if I asked you to write down a tropical cubic formula, which if you come to the problem session tomorrow, you then you will, then this is something you can do, because you're just going to draw, instead of 3 lines for the cubic formula, it will be 4 lines, and we'll be taking the minimum. And we're going to be seeing what the possible options are. Right, so sorry, a question was, what was roots again? Roots is just the tropical hypersurface, because classically a hypersurface of a polynomial in one variable are just the roots of that polynomial. So it's again the same definition, right? Minimum achieved at least twice. Okay, so the point is here, somehow this is an idea that tropical geometry is a bit easier, and you see the shadow there. Okay, questions, comments? To have one more definition before we move on to the connection to algebraic geometry, and that's of a variety. So this is, we might have polynomials in, oh sorry, maybe one question, the red line is, so the red line is the function trop f. The roots are the positions where there are corners. So we're looking for the variety, yeah, so exactly, good. Okay, the variety of f is just those 2 points. Perfect. Okay, now let's go up to multiple variables and maybe more equations. So classically, if I give you an affine variety, I give you a bunch of polynomials and I ask you for the common solutions. Or equivalently, I give you an ideal in a polynomial ring and I ask you for the common solutions for every polynomial in the ideal. If we're over the semi-ring of tropical polynomials, we can still talk about an ideal. So ideals in semi-rings have exactly the same definition, posed under tropical multiplication by tropical polynomials. And then the variety is going to be just the intersection of the tropical hypersurfaces for every polynomial in the ideal. So these tropical hypersurfaces you were thinking of as the zeros of the polynomial, and we're taking the common zeros for every polynomial in the ideal. Okay, so we have, so can we take the intersection to be finite? At the moment, a priori not. So we'll come to that. Well, actually, I won't say it in this lecture, though it is in tomorrow's problem session. And at the moment, one thing that's a little tricky, and I'll just throw it out since it's a commutative algebra expert asking the question, exercise, the semi-ring of tropical polynomials is not Noetherian. Okay. Someone else is asking, why are we taking intersection here? Because we want the common zeros, right? So classically, you want the common zeros. So you're saying, and if you know what an affine variety is, you could write the same definition for usual affine varieties as we did for tropical varieties. Okay, and then a question, what is the variety of 0? That is all of r bar to the n. Okay, so in the same way. Okay, so if the ideal, right, so if the ideal were finitely generated, then you could just take the generators. It turns out that most ideals are not finitely generated. There is, I think we'll come back to this question about finiteness later in the talk, because there's a distinction between ideals in the semi-ring of tropical polynomials and tropicalizations of ideals, which we'll come to in a bit. Okay, let's start on that connection though. And that's this connection to usual algebraic geometry. So we're going to start with a field with a valuation. So valuation is a function from k to r bar, so r union infinity, so that basically behaves like the tropical semi-ring. So the valuation of a times b is the valuation of a plus the valuation of b. the valuation of A plus B is at least the minimum of the valuation of A and the valuation of B for all A and B in your field. And then the last one is the valuation of A is infinity if and only if A is 0. Okay, so you can say this is almost a function that takes your field to the tropical semi-ring. It's almost like a homomorphism, except for this pesky greater than or equal to. So let's do some examples. If you've never seen valuations before, you can do an awful lot of tropical geometry. You can do definitely your first several months of thinking about tropical geometry, just thinking about the trivial valuation. So this is, you know what the valuation of 0 has to be. It has to be infinity, and you just set everything else to be 0. Okay? And you just check that that obeys these valuation axioms. Okay. Another common one is the p-adic valuation. So here we'll take k to be the rational numbers. And the p-adic valuation is going to pull out as many powers of p as you possibly can. So we'll write your rational number as p to the n times a over b, where p does not divide a or b. And then the p-adic valuation is going to be this exponent n. So for example, the 2-adic valuation thirds is, well, I write 20 thirds as 2 squared times 5 divided by 3. And that means I'm saying I can see a 2 squared, so the valuation is 2. The 3-adic valuation of 5/12, I say I write 5/12 as 3 to the minus 1 times 5 divided by 4. And it's minus, I get the exponent being minus 1. So I get some examples. I can see some questions. So where does the idea of valuations come from? Maybe one way to think about it is it's a abstraction of a log. So it's an abstraction to more general fields of the concept of a log. Because log of A times B is log of A plus log of B, and log of A plus B is related to, to log of A, the minimum of the, well, so max actually of the log of A and the log of B. And then, and yes, the first property of the valuation will give us that, well, that, yes, from the valuation axioms, 2 exercises, which if you come to the problem session you will do tomorrow, are the valuation of A is the valuation of minus A. And someone's asking, do we need to require that the minimum is achieved in 2 if val A and val B are different? And the answer is no, you don't have to require it, but it's true. It follows from the axioms, right, as someone else is pointing out. Great, good. Okay, here is the reality check. Are we on the same page? How good are people at your powers of 2? The 2-adic valuation of 65536 divided by 7 is 310. That's a, okay, we'll wait till it converges. Oh, it's not converging yet. Okay, most people, so we have enough people who've played with computers and know that 65536 is 2 to the 16. So max into the old days. Yeah, okay. Or someone who did the cheat of log 2 of 65536. Very good, yes. So this valuation is indeed 16. Fantastic. Okay, let's do another example. Let's look at the Puiseux series. So this is a popular field to use in tropical geometry because it's somewhat concrete to write down examples, but it's also algebraically closed. So this is the Puiseux series. So what we do is for all n of Laurent series in t to the 1 over n. So with the 2 round brackets, that means Laurent series, so power series, but we're allowed negative exponents. And then I'm going to allow fractional exponents. So any given Puiseux series can have fractional exponents, but those exponents have to have a common denominator. And then this is a valued field. And the valuation is just, I write out my Puiseux series and I take the first exponent, the smallest exponent that shows up. So the valuation of this 3t to the half plus 6t squared plus 8t to the 5/6 plus 7t to the 27 over 6 plus dot 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 is going to be a half. Okay, so those are 3 good examples anytime I say valuation to think about. Okay, so here's the I've already said we had one important definition, which was tropical hypersurface. Here's the second most important definition of this lecture, and that is the tropicalization. So I'm going to start with a polynomial over a usual polynomial ring, so with coefficients in a field K, and I'm going to tropicalize it, turn it into a polynomial, a tropical polynomial in the semi-ring of tropical polynomials. And the rules are, we're going to turn addition into tropical addition, multiplication into tropical multiplication, and every time I see a coefficient, an element of my field, I'll take its valuation. Okay, so those are the rules. So to be more formal, I'll use multi-index notation. So when I write x to the u, it's x1 to the u1 times x2 to the u2, all the way up to xn to the un. So if I have a polynomial, f is the sum of cu x to the u, then trop f will be, I just turn addition into tropical addition and multiplication into tropical multiplication. So I get the tropical sum of the valuations of the CUs, tropical times x to the u. Okay. As a function in usual arithmetic, this is the minimum of the valuation of CU plus x dot u. Okay. Why is it x dot u? Because this is x to the u tropically, and you know that x1 to the u1 tropically, that means x1 tropical times x1 tropical times x1 u1 times. So it's really, in usual arithmetic, u1 times x1. So when I see x to the u tropically, I know that I read that as u1 times x1 plus u2 times x2 all the way up to un times xn. So otherwise known as x dot u. Okay, so to see some examples, if I have the function, the 6x squared plus 5xy plus 4y squared plus 3x plus y minus 2. Here we're over q adjoint xy with the quadratic valuation. Then I say to myself, how many powers of 2 divide 6? That's 1. How many powers of 2 divide 5? 5 is odd, so I write a 0. 4 is 2 squared, so that's coefficient becomes 2. 3 is odd, so I get a 0. And well, that's 1 times y, which is odd, so I get a 0. And 2 is 2 to the 1, so I get a 1. Okay. And then you'd notice that really I could have, 0 is the multiplicative identity, so I could have actually not written the 0. So I could just write 1x squared, 1 tropical times x squared, tropical plus xy. And I could have and probably should have written x tropical times y here and so on. And
do you have any question, Diane, about fractional real exponents?
So here we're trying to do algebraic geometry, so we want to just think about things in the polynomial ring. If you wanted to sort of go into a more analytic geometry, then you could maybe think about fractional exponents. Real exponents takes it into a slightly weirder world, but so for now, for the purposes of this week, we are going to my exponents are always going to be integers. I might, for this talk, I'm going to stick in the polynomial ring. You might go to the Laurent polynomial ring and allow negative exponents. So in principle, you could generalize them, but it depends on more or less what category, what world you want to live in. Okay. Let's do one more example. So this one looks a lot scarier, but is actually simpler, right? So I have something times x plus something times y plus something. This is with coefficients now in my Poisson series. But you'll notice that the somethings all start 1 plus minus 7 plus. So this is t to the 0 plus minus 7 times t to the 0 plus t to the 0. So the valuations are all 0. And I didn't bother writing the zeros in front of the x and the y. So it's just our friend from the previous, a few slides ago, the equation of the tropical line. Okay, so that's tropicalization. So maybe we'll just take a moment again give you a moment to see, here's the definition. Can you write, so reality check, what is trop f for this equation? It's a good point to ask if this exercise is not clear. So a question saying, tropicalization always use the quadratic valuation? No, you get to choose what field you're working with. So you start with a valued field. My examples, so we've seen examples now where the valued field was Q with the quadratics, and we've seen an example where the field was the Poisson series with the Poisson valuations. And, right, excellent question. So we had a question, will we have problems distinguishing between polynomials and polynomial functions? This is not the same. This is actually dear to my heart from my actual research program at the moment. We are going to think about, for the purposes of today, you can regard them as the same. I guess particularly when we come to, say, Felipe Rincon's lectures in a month, you will need to know about the difference between them. Right. So it looks like we're starting to get some answers. So let's see if they agree, whoops, if they agree with me. So what I think is 2 tropical times x squared plus 1 times x times y plus minus 2. So that looks to be what people who've been writing answers in the chat have been saying. So hopefully everyone agrees. And it's a good point to ask a question. Okay, so that's tropicalization. And I'm looking for the common solutions in affine space, which is just k to the n. So just looking for the x and k to the n for which f of x is 0 for all f in the ideal. So what's the tropicalization of x? I'm just going to tropicalize the ideal. So that just means apply trop f, which we just learned how to do on the previous slide. So we apply the tropicalization to turn f into a tropical polynomial, take the ideal in the tropical semiring generated by those polynomials, and take the variety of that. So I just intersect over all g and trop I of the variety of g. So this is just trop x is the variety of trop I. So we just, again, the tropicalization procedure is we turn multiplication into addition, addition into minimum, and take the valuation of coefficients, and then we just do this polynomially wise, and then we just take the variety. Okay. So 2 questions. How can we define I of V of I in tropical algebra? This is it's to a certain extent, this is an open research question. And you will, I think, come to Felipe Rincon's lectures in a month for one version of this. Does it make a difference if I has nilpotence? So I think for the purposes of what we're talking about today, classically, we're really in sort of classical, very first course in algebraic geometry. We're just seeing the variety structure. You're going to see more as things go on, and maybe we'll say a little bit more on Thursday about where the difference is there. Okay, can we take the generators of the ideal I or every polynomial? You have to take every polynomial in the ideal. You will not get the right answer if you only take if you only take the generators of the ideal. Then another question, what are the differences between the tropical variety and the tropicalizations of the variety? A tropical variety, what someone means by that is going to depend on the speaker. The tropicalization of a variety in this sense means what we've just said. So if we have a subvariety of an affine space, a torus, more generally a toric variety, everyone will agree on this. What we mean by tropical variety depends a lot more on your context. So you have to, so how, then someone's asking, how do we calculate it if we have to consider all the polynomials? Good question. I'll say a bit more about that on Thursday. Yeah, but it's actually not as bad as you would think. Okay, let us come to the punchline for today though, which is the fundamental theorem of tropical algebraic geometry. Okay, so this is the fact we're going to start with a subvariety of affine space. And so it's going to be given as the variety of an ideal. Then the tropicalization, we just gave a definition. I gave you the definition that said tropicalize the ideal, take the variety of that. But instead, I claim what we could do is we can take the image under the valuation. So I've got the closure, where by closure, I mean the closure in the usual topology. So usual Euclidean topology on R to the n. So we're going to apply the valuation coordinate-wise. And so if I have a point x in my variety, x has coordinates x1 up to xn, x1 up to xn are elements in my field, I can apply the valuation and I'll get a vector in R to the n, or R bar to the n. I take all of those vectors as I vary over all points of my variety, and I take the closure. Okay, so that's the closure of the valuation of x, and the claim is that that equals the tropicalization. Okay, I've put a star here because this is not quite true. It's only true if my field is algebraically closed with a non-trivial valuation. Okay, otherwise, we might get gaps. If you think if I took the trivial valuation, then I'm going to get 0 no matter what. It wouldn't be the pictures I drew before. And if I took the p-adic valuation, well, I could only get integers here. If I took the p-adic valuation on Q, I could only get integers. So I would not get the pictures I saw before.
There are 3 more questions, Diane.
Okay, yes. So let's see, is there an abstract definition for a general variety? So I suspect, I think, for curves, we're going to see definitions that are closer to an abstract definition, not from my talks this week, but in later weeks, I think starting in 2 weeks with Matt Baker. So the answer is, in some sense, there isn't quite a definition of a general variety there. So someone is asking, so the question about k-points, we're going to wait for a moment, and because that's going to be what I say next. And what topology are we taking the closure in? That is R to the n, yes, the standard topology. So Euclidean topology on R to the n, extend that in a natural way to R bar to the n by putting neighborhoods around infinity. Yeah. And so let us, before I come to that last question, let me come to, who was it, Aaron's question, which is, what do I mean by the points of the variety? There, yes, I was meaning the k-points. I had, remember, before we started asking questions, I was saying I had an asterisk here because this is actually not quite true. What I should really say is it's the closure of the valuation of the L-valued points, where L is an arbitrary, algebraically closed, non-trivially valued field extension of K. So what does that mean? If you have a field that is either not algebraically closed or does not have a non-trivial valuation, so has the trivial valuation, you choose a field extension that respects the valuation on the original field, and you do the same definition as I gave before. You take, so by L-valued points, for those who don't know that, you can take it here as just meaning X was the solutions to a bunch of polynomials. If my polynomials have coefficients in K, well, every element of K is an element of an L, so you could also look at the solutions there. So I just look at all solutions in L to the n, or affine space over L, to my original equations, and then just apply valuation coordinate-wise to that. And it turns out it's kind of one of those miracles of this subject that it doesn't matter what field extension L you take. So just as a reality check here, first we'll do a quick example. We have, if I take X to be the variety of X minus T, Y minus T squared. So here I'm thinking of this in the variety in A2 over the Poisson series. So X is just one point, it's just the point T comma T squared. If I tropicalize the original way, so the definition of tropical variety I gave was tropicalize the equations. This definition, you could say, is tropicalize the points. And the fundamental theorem is we get the same answer no matter which one we do. So you can see some of the equations are, we get X plus 1 and Y plus 2. A priori, we have to take an infinite number more. It turns out in this case, a finite intersection is okay. And then we're going to get the intersection of this. This is the minimum of X and 1. So X has to has to be achieved at least twice. So x is 1. The minimum of y in 2 has to be achieved at least twice. So y is 2. And so we get the point 1, 2. But you can see that this is exactly the valuation of the point t, t squared. Okay, so this is the baby easiest example of the fundamental theorem. Okay, let's see one more example though, which is...
There are 3 questions, or 4 at this point.
Okay, origin of the word tropical, I'm going to leave for a few more minutes until the talks thing. Is a single point closed? Yes. What if we consider different valuations? Then you might get different answers. And you have to think about what other valuations you're going to put on the Poisson series at this point, where maybe you'll put the trivial valuation. No matter, but the theorem says you choose the valuation once, and then it'll be true for that valuation. So it'll be true if you had a variety defined over Q, you'll get 1 equality for the 2-adic valuation, 1 for the 3-adic valuation, 1 for the 5-adic valuation, and so on. And yeah, okay, so someone's already answering. So this size equals makes more precise. Yes, that was in the last. Okay. Yeah. Okay, so I guess someone's already answered. Someone asked where did tropical come from? This was the tropical semi-ring actually predates tropical geometry. It's one of the pioneers in the max plus algebra, which more in computer science, was Imre Simon, who lived in Brazil, and this was a French view of Brazil to say, it turns out he actually worked in Sao Paulo, so he had to cross the tropics to get to work between his house and his office. But yeah, let's just finish this with one last example of the fundamental theorem. This is the line x plus y minus 1 in A2C, where we have the trivial valuation. So I'm going to have x is just a line, it's parameterized. We need to have x plus y minus 1 equals 0, otherwise known as y equals 1 minus x. So it's parameterized by the points a, 1 minus a with a and c. Okay, so this is if I think about the c-valued points. However, on the previous slide, and I think this is the answer to Carl's question, we said we had to take if my valuation was trivial, I had to take a field extension with a non-trivial valuation. Okay, and I've just chosen the Poisson series as my choice for a field extension here. Okay, so when I apply the tropicalization, I have to take I'm going to look at the valuation of A, valuation of 1 minus A, when A is any Poisson series. And then I might have to take the closure because Poisson series only have rational exponents. Okay. And now we'll see the questions and people asked at the valuation slide. We're going to use this fact that the valuation of A plus B is the minimum of valuation of A and valuation of B if they are different. So if the valuation of A is positive, the valuation of 1 minus A, valuation of 1 is 0, valuation of A is positive, so the valuation of 1 minus A would be 0, and we'll get the positive x-axis. Okay. The valuation of A is negative, the valuation of 1 minus A is going to be the minimum of 0 and the valuation of A, which is negative. So we'll get this line y equals x is negative. And then lastly, you have to think, okay, what if the valuation of A is 0? And then it's going to depend on what their constant term is. A is a Poisson series. If the valuation of A is 0, it's going to be a constant term plus some higher order terms. And the bits we're interested in, the bits that don't just give the 0, 0, are when A is 1 minus B. Because then when this 1 minus A will cancel the constant term and you'll get something whose valuation goes up here. Okay. But the point you're meant to take away from this is when we tropicalize the equation, we got x tropical plus y tropical plus 0, which was the tropical line we saw before. So I should have really drawn the 0 infinity and infinity 0 at the top here. And this is exactly the same picture we're seeing. So this is an example of the fundamental theorem of tropical geometry. Okay, so maybe this is a good point to stop. In my next lecture on Thursday, we'll see that tropicalizations of varieties have a lot of structure. And then if you stick around for that, or just come back next week where Renzo Cavalieri will tell us some applications in enumerative algebraic geometry.